Hello everybody and welcome to the student revision tutorials for specialist mathematics. I'll be your host today, James Mott, and in today's session on calculus, we'll be looking at reviewing how to use the implicit differentiation command on CAS, how to unpack and solve related rates problems, and also from there look at differentiating parametric equations, and then all throughout we'll be looking at how we apply these things to some exam style questions. To perform implicit differentiation on CAS, we can go through our menu, in particular through the calculus menu, and there's an option in there for implicit differentiation. So if we want to actually work out what the ydx is, the structure of the implicit differentiation command, impdiff, is we first of all have to type in our equation, followed by comma x, comma y. So x is our independent variable and y is our dependent variable. So think of like x as what we're differentiating with respect to. If we want to work out the second derivative, we can simply put a 2 on the end there, so a comma after y followed by 2, and that'll spit out the second derivative for us straight away, which is really handy in exam situations. So a typical exam style question is like the one above. So we want to try and find the equation of tangent of this particular relation at the point 0, 1. So there's quite a few bits involved in this, so we're going to try and unpack this first. So whenever we try to solve a question, we always ask ourselves, what is it we're trying to find? In this particular one, we're wanting the equation of a tangent line. Right? So in order to get that, we need to work out the gradient, because we have the point 0, 1. We've got x1 and y1. We need our gradient m. So to do that, we need to actually differentiate this guy. Okay? So to differentiate this relation here, to get the impdiff command, we can go through menu, into calculus, and then all the way at the bottom, we keep on scrolling, we eventually get towards implicit differentiation, E. Okay. Now, as a little shortcut in the exam, rather than having to scroll all the way to the bottom, once we're in the calculus section, if we press up at the top, it'll take us straight to the bottom of our sub-menu. So that's a little quick way of getting towards that command right at the bottom. Okay. So from here, we can type in our equation. So 4y plus 3 times x squared times y, making sure we put in the multipliers in between all of our factors. That's 5 times x is equal to 1. Now I want comma x, comma y. And that's spitting out the ydx. Okay. Now, we want to actually work at the gradient at the point 0, 1. So we could take our output and substitute in 0, 1, or if we want to be super efficient, after we've typed in our equation, comma x, comma y, from here we can actually substitute in our x and y straight away. So to do that, we need to put in our vertical line. So control equals, brings up a little submenu. There's our given or such that symbol. Now we want to type in x equals 0 and y equals 1. So we can go x equals 0. Now, to put in the second condition for y, we need to put in a space here. So to put in a space in on CAS, at the bottom of our keypad, next to our x, y, and z, we have the space button. So you can press space, and then on the non-QWERTY keypad, we need to try and figure out how we type in and. There's A and D, and once again, space. And then y is equal to 0. So y is equal to 1 is the question. Okay. And so everything there is in neat text. Press enter, and then we can get our gradient m. Okay. So half the challenge is done. We've found our gradient. Now, the main goal is to find the equation of our tangent line. So a neat little way to actually find the equation of a straight line, we've got the gradient, we've got the point. What we can do is bring up the solve command and think about typing in the equation of the straight line with a point. So we've got y minus y1, in this case it's 1, is equal to our gradient from above, 5 over 4, times bracket x minus 0, whoops. And we want to try and rearrange this and solve for y, so we get y by itself. And if we do that, we get the equation of our line at the point 0, 1. That's just a neat little way of finding the equation of a straight line given gradient and a point. So, related rates. Before we launch into it, I thought we'd take a little step back, back to year 9 or year 10, just as something sort of as a warm-up here. Okay. So think about in year 9, year 10, we went to sort of convert from meters per second to kilometers per second, or converting one rate to another rate. Often in this sort of setup, we're given a rate, in this case, meters per second. We want to go towards kilometers per second, and we need to think about what is it that we need in order to convert from meters per second to kilometers per second. So we can sort of think about the units as like a fraction, and thinking about what units do we need to cancel out our meters and to introduce kilometers into the question so we get kilometers per second as a result. And it's this sort of idea that can help us engage with such questions with the related rates. If we think about balancing units, that can help us identify what we need to actually solve such a question, and also check our work as we go along. Okay? So related rates, all it is just an application of the chain rule. So for example, we might have dV dt, which could be dV dr times the RDT, where V is volume, radius, time. Right? So we think about the units like before, we could have volume over time, and thereby if we want to try and figure out what volume of time is given, we might be given the RDT, such as length over time. We need to figure out in terms of units what we need. So it could be we require volume over length just to get rid of, to cancel out these length units. So we're left with volume and time. Okay. So in this question, we have an elevator that's moving upward, and there's some person standing 50 meters away from our elevator. So the person is looking up at the elevator, and when the angle of elevation is 5 or 6 radians, we're told that the angle is increasing, or the angle of elevation is increasing at a rate of 0.02 radians per second. And we want to know what speed the elevator is rising at when the angle of elevation is 5 or 6. So there's a lot going on here. So one thing we need to do is actually unpack this question. So whenever we are given a worded question, the way we answer the question is to ask ourselves a series of smaller questions. Firstly, what is it we're trying to find here? So typically it's always like at the end of the question itself. So in this case here, ultimately we're after the speed of the elevator. Right, so because the units are given as meters per second, we can think of it as we want to find the rate, the xdt, in meters per second. What are we given in the question? What information are we given? Well, the rate we're given, and that's what we should be looking for, what rate it is. We're given the rate of 0.02 radians per second. So it's kind of like d theta dt, well, that's radians per second in terms of units. So if we think about the idea of trying to balance units, right, we've got radians per second, we want meters per second. So what do we need in order to cancel out these radians down the bottom and to introduce meters at the top? Well, we do need radians at the bottom and meters at the top. So that means we need dx over d theta. Okay? So this sort of process that we can go through to identify what it is we need to know in order to actually work out this question. Right? So in order to actually work out dx d theta, we need some sort of relationship between x and theta. So from here, we can take a step back and look at the diagram given to us. So in the original diagram, we had 50. We've got our angle of elevation here. Right? And ultimately, the elevator is moving upwards. So you can represent that in this sort of diagram here. There's our 50. There's our angle that the person's looking up at. And we have some sort of length of which the elevator is at. So we've got a right angle triangle. Back to year 9 Socratella. So important, so crucial. We can see that we've got the opposite over adjacent. So therefore, we can construct this tan ratio here. And altogether, we want to try and get x in terms of theta. So we can say that x is going to be equal to tan theta. Okay. Now, I'm going to define this as x, so x is equal to 50 times tan theta, and defining it using the assign commands. So again, that's control template button to bring out this little blue symbol here. Now, to get our theta symbol, if we press control and this book button, the catalog button, that brings up a whole list of symbols, and there's our theta symbol there. Now, as you're working through this, you may find that it might be easier to use a letter down the bottom of your keypad, maybe a T. But just for today's session, I'm just going to use theta just to make sure it's a bit clear that it represents the angle. All right, so we've established we're trying to find the x dt. All right, in the question, we're given the theta dt, and we just found x in terms of theta. All right, so we want to try and summarize all of our information. So maybe on either a new page or below and you're working out on your book or on your piece of paper, you might just want to try and summarize all the information given to you there. So putting this all together now, we've got, we want dx dt. Right, we know that's going to be dx d theta. So we're going to differentiate x. So we're going to get that through the menu calculus derivative. So I'm going to differentiate with respect to theta. Once again, using the template via the catalog button. There it is, in x. Now, x is defined before, so that's why it's in bold. And I'm going to times that now by d theta dt. And we know from the information given to us that that's 0.02. Okay. And then pressing enter, right, I've got the x dt is equal to this result here. Ultimately, I want to try and find out what the speed is at theta is equal to pi over 6. So I could either substitute in the value of theta here, or from the very start, I could substitute in theta from here. So highlighting this, pressing enter to bring it down, I'm going to sub in theta is equal to pi over 6. So control equals to get the vertical line. And then I'm going to say theta is equal to pi over 6. And remember, pi can be gotten from the bottom left hand of your CAS as well. Okay. So there we've got 1.33 recurring. If we want it as exact, we may need to check our settings on our CAS. So to check that, we can go to the home page, settings, document settings. I'm in order there. All right. If we want an exact value, if I want to force it as exact, what we can do is actually type in the word exact. And then that appears as normal text. And then we can highlight our previous work and it'll force it as an exact value of 4 over 3. Okay. And actually, the reason why that's occurred is if we have a decimal input, like before, I'm multiplying by 0.02, the output will appear as a decimal. Whereas if I converted that into a fraction, I'd have a fractional output. But in order to force it as a fractional output, we can put the exact at the beginning. That'll make it an exact value answer. All right, another question. So here we've got an ice cube in a freezer that's being pulled out. And then we're told that it's melting at a rate of 0.03 cubic centimeters per second. And we want to try and find out what the rate is. So what the rate at which the side length of the ice cube is decreasing when the side length is 2. And for the purpose of this question, we can assume that the ice cube is just a nice simple cube. Okay. So once again, we want to try and pack this question. So firstly, what is it we're trying to find? Once again, often at the end of the question. So we're trying to find out when the side length is decreasing. Again, we're given units centimeters per second. So we're trying to find dl dt. What are we given? Well, the rate we're given is that it's melting at a rate of 0.03 cubic centimeters per second. So because it's melting, it's going to be a negative rate, and that's volumes per second. And once again, we can go through the process in terms of thinking, right, we've got volumes per second, we want centimeters per second, so what do we need to cancel out the volume and introduce centimeters? So ultimately, we want to try and find the LDV. Okay. So that then begs the question, what is the relationship between L and V? So often these questions can come across as a geometric nature, as we saw before with the triangle. In this case here, we've got a cube. So we can go ahead and think about how we define the volume of a cube. So the volume of a cube, again, using the sign commands, we can define V as L cubed, where L is the side length. And then we can go about finding dl dt. So dl on dt is equal to. So we want to try and find out what dl dv is now. So we should remember, obviously, from earlier on in the year, that that's just going to be 1 over dv dl. So we can find out what that is by differentiating v respect to L, and then multiplying that by the given rate of negative 0.03. Okay. And then we can work out what our expression is for the derivative. There it is. And once again, we want to try and find out the speed at which it's decreasing at L is equal to 2. So from either the answer we just got or what we entered, we can then substitute in L equal to 2. And get our answer back. Now, I'll also just mention that when working through a question such as this on your CAS, you don't have to type in the LDT at the very beginning. Right? You just may want to enter this into your CAS to get the answer. And that's perfectly fine. I'm just including the LDT just to make sure that we're all clear of what's actually being calculated. In the exam situation, though, you can just simply type in this to get your answer. And just making sure that on your piece of paper, you would write the LDT is equal to this number. Okay. Now, another typical VCAS style question is we're pouring salt out of a container and it's forming a shape of a cone. And the salt is being poured out and being added to the cone at a rate of 0.0001 cubic meters per second, incredibly small rate. And we want to try and find out the rate at which the height is increasing when the height is 0.05 meters. Okay. So once again, we want to try and unpack this question, look at the end of the question and ask ourselves, what is it we're trying to find? In this case here, we're trying to find the HDT, because we're given units meters per second. So H here is the height. In the question, we're told that we're adding at a rate of 0.001. So that's our given rate dVdt, because look at the units, we've got meters per second, so cubic meters per second, it's volume per second. And then once again, we want to try and figure out what do we need to cancel out with the volume. Well, we need a volume. And then we want to try and introduce meters at the top there. So in terms of the rate that we need, we'll need the HdV. And then once again, we need to figure out and try and think about how is it that can we find a relationship between H and V. Okay. So we can look at the diagram from the diagram given to us and see there's a right angle triangle in there. We've got H, we've got 45. So we think about the volume of the cone in the beginning. Volume of the cone is 1 over 3 times pi r squared H. Now, at the moment, we can't really work with this because we've got two variables happening here. We've got H and R. So we need to try and figure out some sort of relationship between H and R. So from there, we can look at the diagram. We've got this right angle triangle. We're given the height. We're given the angle of 45. The cone has some sort of radius R. So once again, we can fall back on our good old friend Sophocles and find a relationship between R and H by saying that opposite over adjacent is tan 45, or preferably in radians pi over 4, and therefore get that H will be equal to R, which then allows us to then sub in R is equal to H. So, for example, V given that R is equal to H now makes our volume strictly in terms of height. Okay? I'm just going to redefine that just to make sure when we work with it, we have the volume solely in terms of the height h. All right, we're almost there. So we want dhdv, sorry, we want dHdt. We want to figure out what the hdv is. So that's just 1 over the derivative dvdh. And we're multiplying that by the given rate of dvdt from the question, 0.0001. Okay, we can go ahead and do that. And then also we want to try and find out what the height is at 0.05. So you can sub in a value of h, when h is 0.05, and get our rate of increase straight away there. Okay, and like before, as I said, like in an exam situation, it would just be easier and more efficient just to simply work out what this is going from there. Okay, you don't have to type in the HDT or the initial rate you're trying to find. Okay. Now, with these sort of 3 questions presented to you, we can see there are different sort of forms in which we can work out what that unknown rate is. So, for example, in the first one, the xt theta, that was just a straight derivative. In the second one, with the LBV, we had to flip the derivative. And then in this last one here with the cone, right, once we start to flip the derivative, we also had to find a relationship between R and H here. So in terms of the related rates questions, whilst the structure of them are quite similar in that we're often given a rate, we have to find an unknown rate. The actual, what we need to figure out, what we want to figure out, can be sometimes straightforward. Otherwise, sometimes it can be a little bit trickier and requires a bit more work involved there. All right. Now, with differentiating parametric equations, once again, these are just a straight application of the chain rule. So often we're given x in terms of t and y in terms of t, and we want to try and figure out what dy dx is. So by the chain rule, to figure out what dy dx is, we've got dy over dt times dt on dx. So we're going to flip the derivative of dx dt. Another way we can sort of view this is just simply dividing those derivatives, dy dt divided by dx dt. Okay. So what we can do in this question is we're given x in terms of t and y in terms of t, so let's define them. So once again, we're going to use this sign commands. So x is assigned to negative square root t plus 1, and y is assigned to the square root of 3 times t, and making sure we put in those multipliers between the coefficients there. Okay. So ultimately, we want dy dx. So to get that, we're going to divide by the 2 derivatives. So firstly, let's put in our division symbol. All right. And then up the top, we want dy dt. So we can go to our template button and get our derivative template. And we want to differentiate y with respect to t. And then down the bottom, we want to do the exact same thing with x. T on the x. Right. And notice how x and y are both in bold because you just defined them above. So there's our dy dx in terms of t. And then because we want to find out the slope at t equals 3, we can take our result and then substitute in t equal to 3. And there's our slope. Once again, we could have either substituted in with our result here, or at the very beginning, we could have substituted in t equal to 3 to get our result. And just like beforehand with related rates, you don't have to, like in an exam situation, you don't have to type in dy dx. It's just included here just to make it clear as to what it is we're actually calculating at the moment. All right. And now for another exam style question. Once again, we've got some parametric equations. And now we want to try and figure out the values of t, which its gradient of the curve is negative 2 root 3 over 9. So once again, we need to figure out what it is we're wanting. Right? We want the gradient to be equal to that number given. And in order to figure out the gradient, we need to figure out what dy dx is. So using the idea of that chain rule there. All right. So once again, we can define x and y. So x is 4 minus 3 times sine 2 times t, and y is equal to 1 plus 2 times cos 2 times t. Right. Now, if we wanted to dy dx straight away, right, we can take the derivative dy dt and divide that by the x dt. Right. So at the moment, that's our dy dx. Now, we want to figure out when that gradient is equal to negative 2 root 3 over 9. So we have to use our solve command now. So menu, algebra, solve. We want this guy equal to negative 2 times square root 3 over 9, and solving for t, and making sure that we put in a domain restriction that's given to us in the question. So vertical line where 0 is less than or equal to t is less than or equal to pi. Okay. And we're picking up 2 t values there. So this sort of style of question is typical of an exam where we've got sort of multi-components in the question. Right? It's just not a straightforward derivative, but actually we're doing something with the derivative. Okay. So hopefully you found today's session useful. Once again, if you have any questions, please feel free to ask in the chat. We've got people on hand. But for now, good luck and stay safe during this time. Thank you for watching today.